Alright, welcome back everyone. So this is where we left off in the last part. We have our ODE, we have our differential equation right here, good. And we have our boundary condition. We have two boundary conditions. Boundary condition 1, the flux at the center is going to be 0. And that is true for all curved coordinates. So that's going to be true for problems in cylindrical and spherical coordinates. Because the flux at the center is always going to be 0, it's going to cancel out. So just to give you guys a visual, idea, this is the center of a sphere. So you're going to have a flux coming from this direction, a flux coming from this direction, and you're also going to have a flux coming from this direction, this direction. So they're all going to cancel each other out. So the flux at r equals 0 is going to be 0 because the fluxes from different directions are going to cancel each other out. Good. And is the second boundary condition comes from Newton's law of cooling. So that's how our sphere is being cooled in this problem. So in this part of the video, we're just gonna perform the integration. Okay, we're just gonna perform the integration and maybe use one of the boundary conditions. Let's see what happens. So I have the differential equation right here. So let's see what I can do. I'm gonna multiply both sides by r squared, and we're gonna switch to a different color. So you get r squared here minus r squared times r squared, which is going to be r to the power 4, divided by capital R squared, okay, equal to the ddr r squared dt dr. Great. Okay, our first integration. All right, we're going to perform our first integration with respect to r. Integrate this with respect to r and integrate that side with respect to r. So the left side becomes negative a over k times r cubed over 3 minus r to the power 5 over 5 r squared plus the constant of integration. And let's use a different color for that. C1 is my first constant of integration. Of course, that's going to be equal to the r squared times dt dr. Good. Now, okay, you guys might be tempted to divide everything by r squared and perform the second integration, but I suggest that this point right here is a good time to use your this point right here is a good time to use your first boundary condition. So use BC1, and BC1 stated that at r equals 0, the flux is going to be 0, which means the dt dr term is going to be 0. So by applying that, using that, on the right side you get 0 times 0. How convenient. On the right side you get 0 times 0. On the left side, let's see, negative a over k times 0 minus 0. Great. 0 times, and this also goes away, plus c1. Different color for that. And hey guys, we got c1. We found out that c1 is going to be equal to 0. That's not bad. I'm gonna take it. Okay, I'm gonna take it. So this means that the integrated form of my differential equation, negative a over k, the conductivity, r cube over 3, yep, r cube over 3 minus r to the power 5, r to the power 5 divided by 5 r squared, and that's just going to be equal to r squared dt dr, because, well, we know c1 is 0. Hey, nice job, good one. Okay, at this point we're going to divide both sides by r squared. So we get a, and let's see, once you perform the algebra, this is what you're going to get. R over 3 minus r cube over 5r squared is equal to dt dr. And let me pause for a moment and see if I've made a careless mistake. All right, seems good enough. So upon doing our last integration, we're going to get on the right side, we're going to get the temperature as a function of r is going to be equal to negative a over k r squared divided by 6 minus r to the power 4 divided by 20r squared. And you know what, I'm going to push this aside a little, okay, plus the second constant of integration. Okay, all right, so I've already used my boundary condition 1. Now I need to use boundary condition 2. And boundary condition 2 is actually a mixed boundary condition, also known as a, if I remember correctly, a Robin boundary condition. So the boundary condition says that negative k dt dr, the heat flux at r equals the radius of the sphere, capital R is the radius of the sphere, is going to be equal to h, the heat transfer coefficient, the temperature at r equals capital R minus T infinity, the temperature of air. So let's see, we're going to have to construct both of these terms. This one's going to be easy. What about this one? Good thing we have a dtdr term right here, right? So let's see. Let's see how much I can cover in this part of the video. So for this part of the video, I'm just gonna give you guys the derivative evaluated at r equals r, dt dr evaluated at, well, actually this entire term evaluated at r equals capital R. So you have this guy over here. Let me just no, I'm not gonna copy that. I'm just gonna start fresh because my tablet can be a piece of work sometimes. So negative a over k times capital R over 3 minus r cube 5r squared. And as you guys can see, this cancels out. Mathematics, good. Okay, of course, there's gonna be a negative k here. So there's gonna be a negative k here. So negative k times dt dr evaluated at r equals capital R is just gonna be a times r over 3 minus r over 5. And if you guys like doing a lot of algebra, if you guys love algebra, then you can just combine these two fractions, right? And that's gonna give you 15, 5 minus 3, 2. Let's see, 15 divided by 3, so that's gonna give you 5, 5. Oh yeah, that should be good enough. Let me know in the comments if you guys think I've made a mistake, because I have a history of doing that, so you guys can help me. We can help each other. So okay, I have my left side. The left side of the boundary condition is ready. The left side of the boundary condition is ready. Yay. Now in the next part of the video, we're gonna work on, guess what? The right side of the boundary condition. We're gonna work on the right hand side of the boundary condition. So yeah, just see if you guys are following so far, and yeah, leave a comment, or just leave any questions in the comment, any algebraic mistake you guys think I've made. We're gonna talk about it. Oh, before I leave, we're not gonna, no parentheses unclosed. No parentheses unclosed. Am I right, boys? All right. Yep, so thanks for watching, and I'll catch you guys in the next part of this video.